So this talk is going to be a little bit interesting for me to give because I want to talk about how systems are responsive. And I find it's really important that if you don't respond in a timely manner, things go wrong. And this is kind of typical of systems that we have, is we have to react. Can we turn the levels down a bit, please? Okay, is that any better? Okay, so we need to be able to respond and have our systems react in the right sort of way. So kind of first up, I want to talk about what it means to be real-time. We hear this a lot, and real-time has got a very specific meaning. So I'm going to separate it out into three different types. First up is hard real-time. This is if you were in the military and you're designing something, and if it doesn't meet its response time goals, it is considered a catastrophic failure. This example here is called a goalkeeper. It's the last line of defense on a Navy warship. Whenever everything else has failed when a missile is incoming, this thing has got the job of taking that missile out in the last few microseconds before it impacts. So you imagine it has to be very, very real time to get this sort of stuff right. It can fire 4,500 rounds a minute, computerized, guided by radar to try and hit what's coming in. More of what we're doing, say, here in London is working on finance apps quite often, and it's the softer sort of real time where you want to be very reactive, you want to respond at the right sort of time, but if you fail occasionally, it's not a catastrophic failure. It's not a case of everybody dies when that happens. Such a typical finance. But what's kind of interesting is when you need to be fast in the space and need to be responsive, you don't need to be the fastest. You're just not going to be the slowest in the herd, because if you're the slowest, you tend to get picked off. This is a very common thing in trading systems. So don't be the slowest, but as long as you're part of the herd, you're generally okay and you're generally fine. Now, other types of applications, I kind of call them squidgy real-time. And this is your typical user getting frustrated because your system doesn't work or doesn't respond fast enough. And there's actually lots of great studies that have been put out by the likes of Google, Amazon, Shopzilla, where they've improved the responsiveness of their systems. And as a result of improving that responsiveness, they end up having made more money. And this has become something that's very, very interesting. I worked on call centers in the 1990s, and I discovered that systems that are responsive are so important to making the users feel happy and making sure they're getting a good level of service. So as I'm kind of talking about when we talk real-time and responsive, we're probably in the last two categories when we're looking at things. Now, also, when people are working on these types of systems, quite often they're not aware of what can go wrong and some of the responsive issues that we have. I'm going to try and highlight some of that because quite often it feels a little bit like this. We work on our systems, we're kind of digging away, and we have no idea what we're just about to dig into. So, what are we going to cover? We're going to cover 5 basic areas here. I want to talk a bit about how we test and measure systems. I want to talk a little bit about the theory behind what's going on. I'm going to actually show you some graphs and some equations, so I apologize for that up front. But it's very useful for understanding what's going on. And I'm going to talk about some things that I've actually seen in real-world systems and got some data that we can dig into. And it's great fun to look into what causes stuff. Then go into some common pitfalls that we all approach and finish off with some algorithms and techniques you can take away. So I don't want to just talk about the theory of this. I want to leave you some real things you can take away from this at the end of it. So let's start off with being able to test and measure. So let's say I'm Lord Vader and I've taken delivery of my new Death Star and I want to test it. Is it going to be responsive enough? Quite often we don't test enough, but we should be. We should at least be having a means of doing distributed testing on our system and finding what's going on. We should test in a number of different ways, especially in the modern world. We quite often have issues where we have one client that hits us incredibly hard, or we've got many clients that hit us. These are two quite distinct scenarios, and so we've got to think about this because we'll find the different contention points in our systems, and these contention points really matter as we go forward. What's really important when you start doing the testing is you need to make sure you're measuring correctly. And for example, if we were measuring, and if I had my measurement happening over here, quite often I'll be finding all the flaws in my load generation system. And that's not what we want to be measuring. We want to measure the system under test. And so the best way to do that is to have a third-party observer. And in this case, a third-party observer can look at network traffic, for example, log all of that network traffic, and then from there you can work out the true responsiveness of your system. Now, that can be some complicated hardware to do that. It may just be a box that's running in promiscuous mode on a network, sucking up all the TCP packets that you go and look at again later. There's lots of interesting techniques for doing that. So I just want to lay that out, that we need the correct measurement up front. I really recommend that if you're going to get into anything with a serious response time guarantee, and just even basic systems, you need to be doing continuous performance testing all the time. We do continuous integration now as a common practice, but continuous performance testing is just as important on this to make sure you know when you've got problems with your system. It's all about feedback cycles. If you discovered you've broken it this morning, you'll know the code that's broken it. If you work on a project for a year, and then at the end of the year you discover you got a performance problem, where in that entire year did you create the problem? The sooner you catch it, the sooner you can fix it, because you can deal with it. And record everything. So people will talk about sampling as a problem. There's lots of issues with sampling, and we'll see why quite soon. So whenever we catch our data, people will quite often talk about the average response time of a system. And the average response time of a system is really nonsense. It has no meaning at all. When you talk about averages and having any sensible meaning, you must be having a standard distribution. And response times from systems do not have standard distributions. If we look at this example here, we've actually got a positive skewed distribution and it's bimodal. That is not anything you can deal with sensibly using standard deviation. Interestingly, when people start talking about averages, what do they really mean? Well, they typically mean the mean of something. That's the average. That's add them all up, divide them by the number of things that there actually are. In this example, the mean is nowhere near the interesting stuff. There's interesting stuff out on both ends, but the mean's coming out in the middle. Then we look at the median. Again, it's even less interesting than what's going on here. The interesting value for me is the mode, the one that's happening most common. And actually, when I'm trying to clean up a system to make it behave better and respond better, I want to move everything that's not on the mode down to the mode and improve it. And sort of getting that sort of stuff is important. So I just want to set that as a view up front, that we're not looking at averages, because averages tell lots of lies. So here's a simple example. Let's say I have a trading system, and it's responding in 50 microseconds typically. That's its typical, that's its mode. Now all of a sudden I introduce a 20 millisecond garbage collection pause happening once a second. What happens to our average? Well, whenever that goes forward and happens, for 25 milliseconds, if you're going at 1 per millisecond coming in, 25 of those events is going to have an average latency of 12.5 milliseconds. All of a sudden, our average latency for everything is now up to 300 microseconds. This is useless information on both fronts. We're not seeing the really bad pauses from this number, and we're not seeing the typical case. So the average is not good. And if you're trying to do SLAs and you're reporting to your boss, you're reporting to your customer, you end up feeling a bit like this, because it's silly. It's just absolutely nonsense. We've got to report this in a better way. So forget averages. We should be thinking about percentiles. Well, what are percentiles? Well, Gil kindly lent me this slide from one of his customers. And what we're looking at is looking at what percentage of any given response to a system fits into a certain percentage range. So like 90% of them are below a certain level, 99, 99.9, and you talk about the different nines that's going up. And if you look at this real system was from a customer he had who knew they had a problem, but they're trying to work out how bad was the problem, what could they do. So they were seeing pauses. And when they measured the system, the blue line is what they were measuring in their system as it stood, this one over here. And actually seeing a line that's all jerky like that, that tells you a lot straight away that something's not right in your system. And what Gil has termed is this thing called coordinated emission, is whenever you get a pause in your system that you can't control, you skew all of your averages and all of your percentiles so much, because when that pause is happening, you're not doing any work in the system. And because you're not doing any work, you're not adding up all of those values that should have been there. Like go back to my example of the 25 millisecond pause when you've got garbage collection, you've actually missed 25 events. And many systems, when they load test or performance test, they stop at the point when that's happening. They're not actually tracking that, and then those numbers get hidden and you lose out what's going on. So I recommend go look at some of Gil's talks on latency measurement, and coordinated emission is a great way of describing a lot of what's going on. So Don't deceive yourself, measure correctly, be aware of what latencies are about. Having set some of that grounding, I want to move on a little bit now into some proper theory. This is the kind of scary part. But we may have all heard of queuing theory. It's an interesting branch of probability math, and we'll hear about J-curves in systems. And what this is your typical J-curve, whereas if I increase load or I've increased utilization on a system, my response time follows that curve. This is your kind of typical thing that most people will see in the system. Well, why does that happen? This is kind of interesting. Well, there's some interesting math behind that. And for the example we just looked at, we use a thing called Kendall notation here. And what this M, D, and 1 is standing for is I have got an arrival rate, which is the first letter. The type of arrival characteristics, this is a Markovian arrival, so it's exponentially distributed in what's going on. It's quite unrealistic because there's no memory effect, but it gives us an easy way of doing the math that's coming up. D stands for the service itself and the fact that it's deterministic. A service may not be deterministic. In fact, most real systems are not deterministic because people don't design them that way. But let's say we do try to design them to be deterministic because it's the one thing we can control. We struggle to control our arrival rate, so we've got to expect almost the worst from that. And the 1 just means we have one instance of the service at the end. So let's plug that into some math. And using this formula, I can work out what my mean response time will be for any given utilization of my service. And by utilization, I mean if I've got a CPU, a disk, an algorithm, anything that's a service, if I use it to a certain percentage of its capacity, I know what its utilization is. And so the two things we feed into this is the service time and the utilization. But kind of interesting, if you look into what utilization actually is, it's the arrival rate times 1 over the service time. So service time is the key thing in what's going on. Now, I'm not going to ask you to remember the math, but the thing to remember from this is, so let's say I'm out and I'm at the 90% point over here. So I'm using my system at 90% capacity. My response time is probably 10x what it is in the case where it's very low utilization, where it's kind of less than 20% utilization. Now, if I half my service time, so I rework my code, I make my system twice as fast as it used to be, what happens is you go from the 90% utilization down to the 45% utilization, and half that again because you've halved the service time. You now have a system that is 10 times more responsive by making it half as long to run the service. And this is where the math starts getting really interesting. I love problems like this. You find the system that's around high utilization, you make it a little bit faster, and all of a sudden it's responding so much better, it's so much quicker. And it's all to do with probability theory and queues forming. And this is all assuming queues are unbounded and things are allowed to build up like this. And queues are everywhere. We cannot avoid them. So, pro tip here is if you want a system to be responsive, make sure you have sufficient capacity. Make sure your utilization levels are not going too high. Because if you kind of go back to this, right up until beyond 60% utilization, it's only going to be twice as unresponsive as in your best case. At 80%, you're going to about 3 times it, but it starts getting really, really bad after that quite well. So beyond 80%, things are very, very bad for most systems. And this is one type of curve. You can have other ways that things arrive, but generally they all have this sort of shape, and they just move around a little bit depending on some of the characteristics. Interestingly, this applies to anything. This applies to your teams. If your team is running at close to 100% utilization, their response time to any incoming request is going to be horrendous. If there's any project managers in here, you really should go read queuing theory and wonder why your projects are getting screwed up. You feel your team has no slack, there's a very good reason why you're not responding to your business, and you can't run away from the math. Math doesn't lie, and it hunts you down. So, we should be bounding queues if we want to have a good SLA, and I'll get on to explaining that more later on. So, we also, if you've been doing a lot with queuing theory, so a lot of this goes back 100 years, some of the great work of Erlang on telecom exchanges. But then John Little came along 50 years ago, and he actually refined this in a kind of nice way, where if you've got a system in steady state, and the point is the system has to be in steady state where the arrivals and the departures are happening at the same rate, If you know any two of these variables, and it doesn't matter whether it's deterministic, Markovian, Erlang-based, whatever you want, you can work out the third one. So if you know any two of these, you can work out the third. So really, really simple, really, really useful stuff. But let's say we want to go parallel to speed things up. That's what everyone's talking about. The future's parallel, and it is. We're getting many, many more cores inside our CPUs, and we have to be able to deal with that. So let's look at Amdahl's law. Kind of interestingly, Amdahl never actually put an equation in his paper. His original paper, 3 pages of it, had not got a single equation in it. And I talk about Amdahl's argument rather than Amdahl's law and how it was put together. The reason he did that is he was peddling mainframes. And he wanted to discourage people from doing parallel programming because he wanted to show how ugly parallel programming gets very, very quickly. That was his motivation for doing this, by the way, and yet everybody in the parallel computing space keeps talking about Amdahl. But what's the basic tenet here is that if I have any job and I want to break it up to go parallel, I can only break up the bits of it that can go parallel. There's some bits of any given job, usually you cannot make it parallel. There's a serial component. And so in this example, let's say A, I can actually split and run it in parallel across 4 cores. I get a reasonable speed up in the time to do my job. If A couldn't be split apart, but B could be, it's actually not so good. So that's kind of interesting. But actually, you start looking at this in a bit more detail. If even just 5% of your code is the serial component, you cannot get greater than a 20 times speed up, no matter how many cores you throw at it. You basically asymptotically approach that, but you never even get to it. So this is what Amdahl was trying to make the point is parallel programming is very hard if you have got any shared state or any contention that you're having to deal with between threads. The really interesting bit is, this is the optimistic view. It's much, much worse. There's a guy called Neil Gunther who, through doing lots of real-world benchmarks, discovered he couldn't even get close to this. And he came up with universal scalability law, which is really nice. And it deals with 2 things. It deals with the contention and the coherence of a problem. So the contention part of it is exactly the same as Amdahl's part of the problem. You don't need to remember the math. We'll give the slides later on. But the point being that whenever you have contention, you also have coherence delay in making sure that contention is dealt with. So for example, a lock itself, there's a delay in acquiring and releasing that lock, and sometimes can be very, very high. Let's actually take Amdahl's law and take universal scalability law and plug the same figures into them and assume a contention of only 5%, but a coherence cost of 250 microseconds, only 250 microseconds. You're talking here about some basic network traffic to keep some stuff in. Look what happens to your throughput. It doesn't continue on and beautifully going to asymptotically approach a 20x speed up. It barely gets over 10 and then starts going down. Gets even worse again because you're spending more time dealing with the coherence delay than you're actually even dealing with the contention itself. So contention will really screw you up in how this works. So going parallel is one answer, but you can only go parallel with minimal contention and some means of keeping this thing coherent very quickly. So that's all kind of about how we deal with the service, how we queue on it, but what about the service itself? This is the thing we can control. Well, the best thing we can do is work on the service to make sure the order of the algorithm is giving us the behavior that we want. If we want it to be deterministic, we should be going for order 1, or maybe settling for order log n. But anything else is not good in a deterministic service. We need to be thinking in the order of our algorithms, the data structures we use, and that's what will give us a deterministic service. This is basic computer science. So that's the theory over. I'm not going to bore you anymore with that. But I'll talk about some practice. And this is some really nice, interesting, cool practice from a customer of mine who I promise not to name, but they have very kindly let me use their slides. Now, some of my customers I turn up at and they haven't even run a profiler. So fixing their problems is like it's getting on for a joke. You just run a profiler, there's your problem, fix it and move on. It's kind of nice. These guys are actually really good. They contribute to the mechanical sympathy group. They're very low-level guys. They do some really good stuff, and they wanted to take this to the next level. They have a product that they want to take to the next level. So we were measuring their system, and they've got great performance tests and great metrics. Here's some graphs. So I arrived at the beginning of 1 week, and we're trying to work out how do we make this system more responsive. And so this is a graph of what's happening to every single request going through this system at a rate of thousands per second. This was the response times of the system. And you get this messy sort of graph. This is kind of typical. Over at the left-hand side, you've got a lot of bad response as the system warms up. That's kind of typical. We're used to that. Then as it's warmed up, there's all these weird spikes and there's dots all over the place. Where this system, if you actually dig into the numbers, its mode is around about 50 to 60 microseconds in how it's responding. Yet there's outliers in the seconds of what's going on. And there's lots of mess in between. And I love the visual side. You can see there's stuff going on here. And the thing that I love to dig in and find out what that stuff is. What's causing those spikes? What's causing that noise? Well, having dug into this one, first thing I found that was interesting is they're running an old version of the disruptor. They're running a previous version, then version 3. They were using it in the multi-producer scenario. And there's some pathological cases in the disruptor in the older versions where if you've got far more threads producing than you've got cores that are able to run it, it gets into some bad queuing effects that happens. Version 3, I worked on this a lot with Mike Barker to come up with better algorithms for dealing with that. And so we upgraded this, and look what happened. Notice? Just an upgrade of what went on. So we got rid of some of the big nasty queuing effects. The overall system got faster because we improved utilization. But there's some really interesting things going on. Like if you see over here, there's strata happening here. We can see this like over time. This screams out to me, data structures resizing, something interesting is going on. And so I want to dig into that and find out what's going on there. So let's zoom right in. So like, I want to take one of those like interesting little areas. Like you got a spike and some weird noise around there. What's that like when you zoom into it? You start seeing these sorts of things. It's like there's clearly bandings. And like this thing jumped up and then jumped down and there's gaps. And so then we start digging into the logs and find out what's happening at that point. And what we find is those gaps where there's nothing happening here and here, garbage collection would basically come in. You're having young generation garbage collection and we're getting pauses in the tens of milliseconds for that. Now, I'm talking here milliseconds, microseconds, and some people think, well, that's not my problem. I see these problems all the time on different levels of scale. The people who don't have the millisecond or microsecond problem, they've got the multi-second problem, and they're just doing the same things at a different level of scale. So these things exist, and they're completely ubiquitous in how they happen out there. So we dug into this quite a lot, and we wrote some aspects that were aspecting different parts of the code to find out when data structures were resizing. It's a really nice technique to be able to do that, and we spotted that, and we captured the resized things. We logged when it happened and how much time, and it completely correlated with some of what we're seeing here. So we knew this was data structure resizing. So we went and fixed that. Well, the big step up wasn't just the data structure resizing. As it resized, it rebalanced in interesting ways, and that's why it took things longer for a while, then jumped back down again. And things like the key space that you're dealing with is kind of fun computer science stuff to deal with. Also, the reason why we've got those two GC gaps there is, as it's resizing data structures, it generated a whole bunch of temporary objects to do the resizing. So this is kind of all fun. We dug in, we found out what that was, we fixed that. So now, look, we've got a very different view of the world. We've got all of those weird spikes that are very step changes, they're all gone. We've dug into it a bit more. But look, there's this weird strata thing going on now, right across the whole thing. So that's telling me that it's doing stuff. Sometimes it's stuck and not doing stuff, and then stuff is moving forward. Well, drilling into that, it turns out to be the scheduler, the OS scheduler, doing stuff for you. I'm going to touch on the sort of the stuff that it was doing. And whenever it's doing stuff, it can end up running your threads on other cores. And when you've moved your thread from one core to another core, you go to another core and your cache is cold. You have to warm up your cache, and so that makes you much slower. So whereas you may have been down here, you're now up on this level, or you may have been moved across to a different type of core and you're up on another level. So we changed this application and we introduced thread affinity as a script after it was running for a while to pin threads to cores. Boom. There to there, thread affinity. I've seen people say, Applying thread affinity is for sissies and wimps, and you shouldn't be doing that. Those people don't make money. They don't trade and things. I know who some of them are. They contribute to Java util concurrent, and they say you shouldn't be doing this. This makes a difference. It makes a massive difference. Cache misses are your biggest enemy now on modern processors and how they run. But look at that. Now this is getting much better. But see, there's still these weird little spikes. That's GC. That's a well-tuned application just experiencing very, very short new generation collections, but it's still getting you. And then it has effects that ripple on from that. And some of the stuff that's further up, there's all sorts of other nice, weird, and wonderful stuff like lock rebiasing and save points, which I'll talk about in a second. So that's a kind of, it's interesting when you dig into what's going on and where your costs and what's happening. So what are the pitfalls that we can all make? So we're this little guy who's tunneling out earlier in the picture, and he's going to tunnel under the latrine, and things are going to get really bad for him really quickly. What are those things, and where do they come from? Well, let's start at the bottom. Modern microprocessors, they do a lot for us. They're very advanced. But one of the things that they're fighting for all the time is saving energy. They want to have the power envelope as low as possible. So they've got many things to help with that. And they also monitor themselves. So you'll hear about things like P states and C states, where people will have the processor clock down to different frequencies, or it'll turn off parts of the processor when it's running. And by default, these things are all switched on. The whole point being, let's save energy. The problem is, when the processor comes out of those sleepy states, it takes a long time. And those sleepy states, depending on how deep they are, also flush out caches. And the cache has to all be warmed up again. And so they can really make a big difference. There's also other goodies like SMI, system management interrupts. With the BIOS and the underlying hardware, will actually poll the processors for what's going on. Say like, how are you doing? Have you seen any errors? Are you running too hot? All of these sorts of things. This stops your processes from things happening. There'll also be things like hyperthreading and turbo boost, where it's trying to get more out of the silicon that's there. But they've all got impacts. So with hyperthreading, each core can run 2 threads simultaneously. It tries to get that extra throughput by relying on filling in gaps whenever the processor's cache missing. But as it's running 2 threads, it has to share a resource. It has to share things like the decode buffer for instructions. It has to share things like the translation leukocyte buffer for translating virtual to physical addresses. Now, going back to queuing theory, that now halves the amount of stuff you've got for your utilization goes up. So your utilization ends up doubling on those things that are in there, which impacts response rates. It doesn't necessarily impact throughput, but it does impact your response rates. So you've got to be aware of, like, this happens at different levels on the way up. We come up a little bit from the processors. We buy a computer today. It's usually got multiple sockets inside that computer, and the memory's connected to each of those sockets directly. If you need to talk from the memory or from one of the computers over here, these sockets, and the memory's over on the other side, you've got to cross the QPI link. So this QPI link in the middle is basically a network. Inside a computer, you are doing distributed computing today. That's what, so people say you program differently on the machine than you program across a data center. You've just made programming twice as hard as it needs to be. You have to do distributed computing whether you like it or not. Why have one means on a machine and another mean across machines? It just doesn't make any sense. It makes our code more complex, and it's not actually representative of what's going on. So just accept that everything's distributed. Accept that your message passing between this stuff, and things just start getting a whole lot cleaner and a whole lot more scalable. And so this NUMA effect to the memory architecture, again, is a huge pitfall. I can quite often go in and run a couple of scripts on a machine, and all of a sudden the whole system is 3 times faster than it was before. Not 30%, 3 times faster, just by being aware of what's underneath. Then we come up into things like Linux itself. And the virtual memory system can be a huge sort of tar pit of things that slow down your application. There's things like page flushing and I/O scheduling, goodies like transparent huge pages. I'm not going to go into a lot of detail on these, but things like swap and how much free memory you've got left. These things can cause your machine to pause for very long periods of time. And when it's pausing, queues are forming and things are getting worse at that point. So being aware of some of this, we're kind of like saying, no, it's just all magic, you don't need to know. Well, if you want a responsive system, you do need to know, because these things just don't go away. We then get into the JVM itself, and you'll come across these very ugly things called save points. And they're worse than the orcs coming to get you. Garbage collection needs to happen on most JVMs under safe point. And what they mean by safe point is you've got to take the world to a stop the world point, but getting all of those threads stopped is bringing them to safe point. That's what this expression actually means. And so there's many things inside our JVM that requires you to come to safe point. Garbage collection is one of them. There's many others. There's like de-optimization of code. So our JIT compilers are making bets all of the time on how to make our code faster. Sometimes those bets are wrong and they have to undo them. As they undo them, they have to stop everything in the system. And remember back to things like Amdahl's law, and even worse, universal scalability law. When we have to stop everything, it becomes a serial part of our algorithm. It becomes a constraining thing, and getting the coherence on that right can get really, really important. I've seen systems that just cannot get the high CPU utilization because most of the threads can't run at times because there's so much use of locking, so much use of object allocation, and many things that are going on inside there. So look out for things that bring the JVM to safe point, including debugging it. If you need to debug it and get the stack trace, that has to take it to safe point as well. Virtualization is another thing. We're seeing so much of it. But virtualization is a massive tax on system calls. It's not a few percentage points. People say virtualization adds a few percentage points. They're being very economical with the truth. It adds a few percentage points to something that's pure CPU driven that never leaves user space. As soon as you start calling in through that operating system, you call the kernel, it's a virtualized operating system. It then has to call out to the host operating system and all that has to be managed. It can get really, really slow and really, really unresponsive. Like, I've seen examples of this where network traffic was tenfold less than it could have been because of virtualization and poorly set up virtualization. This is one of the goodies I see a lot is people using locks and being able to notify. And I know a lot of people here will talk about futures. Many of the other speakers here will talk about futures. But in many cases, when you are wakening up that other thread, there is a huge cost to that. And I mean huge cost to how you scale your applications. And so underneath, they all end up using things like POSIX, condition variables to signal across threads, or some sort of semaphore mechanism that works across threads. These are incredibly expensive because to use them, you've got to get the operating system involved when you're actually telling another thread to wake up that a piece of work is done. And that is like asking the government to help you to get out through the door. It is a massive tax on what you do. So as soon as you call something like notify or signal or use a future or something in your code that isn't just directly composed, you just have roulette played with the response of your system. And I have seen anything from about 2 microseconds in the best case up to many hundreds of milliseconds and beyond is the cost in some of these individual operations and how they happen. And they add up very, very quickly in your application if you just compose lots and lots of these things together without being aware of the consequences. So this takes me on very well to things like the law of leaky abstractions. Because having all of these things as composable ideas, if they're abstractions, that's brilliant. We need abstractions to function, but they need to be representative of what's going on underneath. If these are not representative, the real underneath starts to leak out, and this becomes a problem. And we cannot get away from this complexity. We can simplify stuff, but we must simplify it in a representative way. Otherwise we get bitten. I like to think of this as mechanical sympathy. I don't need to know the intimate details of everything that's underneath, but I need to know the characteristics of its behavior and deal with it in the correct way. If I was a civil engineer or structural engineer, I would not be allowed to use steel or concrete or wood or anything to build without having some basic idea of what its function and characteristics are to use it. We have people who just use our underlying systems with no clue in what it gives us. And I think this is a real disservice to our customers. We also need to respond in the presence of failure. And this is quite often where a lot of things go very, very badly wrong and they don't cope. Monty Python fans will probably recognize this. It's only a flesh wound. You got to keep going. We need to design our systems that keep going, particularly when things go wrong. I'm going to show you some nice techniques for doing that coming up. So, kind of coming up to the last section now. No more theory, but I want to talk a little bit about what we can do about some of this. How can we make our lives better? Well, first up, we should be doing some form of engineering or science in a way. It's also a craft in what we do, but we've got to respect some of the basic science underneath what we're doing. And for example, I keep seeing so many people benchmark systems, and it's not a clean experiment. If you were to do chemistry and you were to use dirty utensils, it was not a clean experiment. You don't know what's going on. So how can we do this in our systems? Well, starting like at the bottom up, like get those CPUs tuned to the right frequency, turn off the C states, all of these sorts of stuff is very useful. We need to make sure we've isolated certain CPUs so other things aren't running on them at the same time. We could do that with things like NUMA control, C groups, thread affinity. There's all sorts of goodies and stuff. It actually doesn't take long to learn any of this. And getting it set up is actually quite good fun to see the results and seeing it played with. Things like SSDs are making our world really nice now, but they don't always behave the same. There's times when they're clean and when they're not clean. Garbage collection is something that's getting us everywhere. Like, whenever we see some of those pauses in the Linux virtual memory system, it's usually some sort of garbage collection or defragmentation. We see it in our VMs. We see it in our hard disk. We see it in everything. We've got to be aware of this sort of stuff and deal with it in a nice way. Like, you don't randomly just mutate data all of the time. If you treat data as fact-based, append only, keep logging to it, it all behaves so much better. It's also much easier to reason about as well and how it works. One thing I would recommend on any system you're working on, if you're in the Java world and there's alternatives in others, is use a thing called jhiccup. Jhiccup is a simple little tool. It runs, and once a millisecond, it goes to sleep and tries to wake itself up 1 millisecond later. If it doesn't wake up in that time, something stopped it waking up, and it logs that. And you can actually track whether your system is there, ready to run and responsive, and you'll be surprised what it will tell you about your base system and how unclean it is. Run it inside your VM, run it outside of your VM, so see if your problem is actually systemic for the whole platform, or is it just part of the JVM. Nice, simple stuff. And just get used to tuning and playing with this and have fun with some of this stuff. It's really cool. And the reward is the results are so instantaneous and so good that you can get out of this. And you learn so much about what's going on. I've found over and over again the people who get involved in this sort of stuff and start playing with it, they become much better coders because it's not just this whole soup underneath it they don't understand. They start getting an idea of the platform they're working on, they get an appreciation for it, and start enjoying it and getting back to it again. It's not this weird stuff they just don't get anything about. So we also need a profile, but you've got to watch out that many profilers lie. Most profilers take the easy option. They profile at save point. They wait till everything's stopped. And save points happen in most VMs whenever you return from a method or you reach the back edge of the loop. It doesn't just stop anywhere. It stops at very specific points. That quite often is not where the interesting things are happening. So you'll end up finding out that you're getting all this profiling information and it's lying to you about where your code's, because all your hot, busy code doesn't have save points in it. It's kind of great if all your time is spent talking across a network or talking to disk, it'll catch that. But as soon as you go CPU intensive or memory intensive, you're completely missing what's going on. There are profilers coming out now that deal with this. Some of them are built into the VMs themselves, but it's a good thing. What I really like to do is do my own profiling through stuff using basic histograms and timing stuff to start, timing stuff to finish, and add this through your code. Make it also available as monitoring information so you know what's going on. Know about something has gone wrong before your customers do and reacting to it. Don't be the other way around. Your customers shouldn't be your means of monitoring a given system. So, tip here is learn to use histograms. A really good open source one is HDR histogram that's out there. You can log lots and lots of stuff in it. It's got very low memory footprint. It's very, very cheap, very, very fast. And you can print it out with all those percentiles and put it into Excel afterwards. You'll see what your system's actually doing. Now, batching is a subject, I think, it's so misunderstood. And it's a great thing. So we've got our typical J-curve responsive systems. That red line is typically what happens. If you apply some batching theory to your code, and this may sound weird, I'm going to apply batching in a real-time or soft real-time system. Am I bonkers? Maybe I am, but I can tell you that blue line becomes possible when you start applying batching in your code. And many people keep saying batching adds latency. I say, liar or stupid, one of the two. It is not the case, or both. Could very well be likely. So how do we do this? What's an example? So let's say, for example, I've got a precious resource. my disk, my database, anything like that. And I have multiple producers who are trying to use it, and they all go to use it at the same time. They'll queue. Queuing theory will kick in, and they'll queue. And if the time to use it is 1 unit of whatever time, the third one in this case will be 3 units of time you've added to do it. And the utilization has used up 3 units of the utilization of the underlying resource. Now, for example, if I just put a batching thread in between the use of my producers and that precious resource, and that batching thread can drain everything from the incoming queue or ring buffer and put it all in as a single operation, it amortizes that expensive cost. It also gets rid of all the concurrency problems. It's simple to reason about. It's simple to code against. There are structures, like the disruptor being one good example of it. You can exchange sub-100 nanoseconds. There's lots of interesting things out there. So the ring buffer does not become your contention point. It's incredibly cheap. And we can write down. So take a simple example. 10 producers rush to produce at the same time, and you don't apply any sort of smart batching. The first thing to get there goes in 1 unit of time. Next one is gone in 2 units of time, blah, 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 up to 10. So your mean response time on that thing is now 5 units of time, with the worst case experience being 10 units of that time. Now, if I go to the smart batching case and I take the worst case scenario, where the worst case scenario is I only get one thing off the batch in one go, and I stick it into the resource, and then I go back, and the second case I take all the other 9 and put them in. 1 went in 1 unit of time, and 9 went in 2 units of time. And utilization is much better of the underlying resource, and that is your worst case scenario. It's so different just thinking about this. If I'm going to write onto network, it's the same thing, maximize the MTUs. If I'm going to hit an algorithm, it's really interesting how to do this. Like, this is one of the reasons the disruptor is fast, is it doesn't even have to do with going to disk or network or anything. Your algorithms can do this. It's just thinking and doing this. And when you start building systems that can do this top to bottom, it's amazing what you can achieve. I was working with a client out in the US just over a year ago. We wanted to take the Oprah feed, which was peaking at over 11 million messages a second, and they were like, we have no idea how to do this, even on the best servers. We built a system from top to bottom using smart batching techniques, and this thing could ingest the entire Oprah feed on maximum peak on my laptop. It was absolutely fine. It didn't even break into a sweat. And it was easy to understand and easy to reason about and stuff. So you're spending the time to learn this stuff is really, really important. You've got to amortize the expensive costs. It's not just for the responsiveness, it's for throughput, it's for everything, and even the ability to reason about your code. You don't want the complexity of managing that contention. You want to be able to use that resource uncontended in a nice, clean, and friendly way. So if we're now using our resources really well and we're using them efficiently, how do we eventually control what goes on in our systems, and how do we make sure our latencies are there and guaranteed from a response time perspective? Well, what we got to do is we got to keep applying back pressure. You cannot design a system with unbounded queues. If you do, you've designed a system to crash. I can guarantee any system under any interesting amount of load, if all the queues are unbounded, will crash. And the reason it crashes is because it runs out of memory, but it's not the running out of memory. It's a bit like the running out of memory is like people mostly die of pneumonia when they've got cancer. It's the nasty disease up front that actually causes the damage, and the nasty disease is the fact that it doesn't fit in your cache anymore. Because see, as soon as things don't fit in your cache, it runs a least reasonably used algorithm, things start getting evicted. So the poor consumer now is cache missing all the time, where the producer is cache hitting. It just completely unbalances your system so quickly. So let's bound our queues in our system, and we keep applying back pressure. Eventually, you're going to reach the edge of your system. Well, once you reach the edge of the system, you can't get any more traffic in because you're running at your maximum throughput. You're running up to the limit of your SLAs for your queue lengths that are in there. What do? You simply deny more input. It's so much nicer to say, sorry, we're busy, come back later, than take the work and crash. That is not a good level of service. So just designing the systems right through, applying back pressure. Non-blocking designs are wonderful. And I like to think about it as get out of your own way. Like, as soon as you start hogging any resource in your system, and you'd be surprised what your resources actually are, You had a contention point. You then have a coherence penalty, keeping that contention managed. And all of a sudden, you get queues forming. And you also get a serialization point that won't go parallel. So don't hog your resources by being sequential. Also, when you're non-blocking, you can always try to make progress. So even if you're going to use a resource and it's not available, well, do something else. You start thinking this way. As soon as you've locked and tied up something, it becomes a major issue. And one of the fundamental things is about going non-blocking that you can then do smart batching really, really easily. So kind of a pro tip is be really aware that hogging resources has a big problem. And synchronous designs do it so subtly and in such an insidious way that it's really hard to get rid of. I think it's something like a J2E container. You get a request into a servlet. You start calling off to a back-end system. Everything to do with that request is tied up now. The thread's tied up, all the incoming state's tied up. You're waiting on the response coming back. You've got a thread tied up. You've got a socket connection tied up. Then when you get the response, you're going to wake all of that up. That's that notify cost inside the VM. All that state has been held for such a long period of time, much longer than it should have been, which means the garbage collector comes under more pressure and stuff. Basically fired off as a message, smart batch it into your database, get your results back, send it back. Async, so much easier, so much more scalable. And as we go async, start thinking about concurrent algorithms that are lock-free are a great way to not get the operating system involved. Well, and what you do, you agree protocols of interaction. Like anybody at university who used to share a room, if you had someone back to your room, you'd leave the tie on the door and that was your signal, don't come in here. You just leave signals for stuff and you can start having really interesting things with algorithms to make this happen. Don't get the operating system involved if you don't have to, especially now in this virtualized world where the cost of getting the operating system in is absolutely huge. And that way you can beat the notify problem. The other alternative is you end up in bureaucracy and it becomes absolutely silly. So beware those peddling futures. Ask them what's under the hood. Observable state machines. I think state machines are wonderful things. They're complicated. This is my biggest sin here. I'm going to show UML. Nasty, but it's a good way to show a state machine. I'm not interested in the state machines, but one thing I want to point out here is state machines that are observable are incredibly powerful and useful. So if you can just observe a state machine from another thread without any locks or anything else going on, is you can tell progress through your system really well. You can report on progress really well. You can take action when things start to go wrong. You can debug it. You can understand it. It's wonderful. This is a technique that is an enabler to let you build really responsive systems because you can see what's going on and when it's going on. You can get all of those state changes and you can put them in histograms and you can see what's going to be next. So make those observable. Makes a huge difference. Now, how do we deal with resilience and be responsive? So most people, when they have a system that dies, when another system takes over, it's not responsive during that failover time. And that's a problem. Or it's not responsive during a restart. How do we deal with it? Well, if you can run multiple instances of a service and the service is deterministic, if I can sequence traffic to that, I can have 2 instances of my service running. Well, what happens when they respond? Well, both of them can respond back. But if your message delivery protocol is idempotent and you can tell that you've had more than one delivery, it doesn't matter. It just works. This is really nice because you can start doing stuff like one service is on a slightly different CPU than another one. It's on a slightly different memory configuration. It's on a slightly different hardware profile. As a result, the pauses that it will experience will be different from the pauses the other one experiences. And guess what happens as a result of that? Your pauses go out of step, you hide the pauses. You get a very, very deterministic system. And you can go around just shooting versions of them. And you can run even many versions. You can also have other versions running off that are building other views of models and answering questions and doing other interesting things. Quite often, the mutation state is best handled by not having any concurrent access. If you want scalability, that contention point has to go. You need one resource is always operated on by one processing context. So one thread can update one piece of memory. One service can update one database. Whatever it happens to be, you must make sure that contention is managed. It makes it easy to understand, easy to debug, easy to reason about, and it scales. It scales incredibly well. So one thing is, like, I've got to come back to these models here. And I'm almost shocked at times, like, is there a world beyond maps and lists? There is. There's a huge world, and it's a wonderful, rich world of data structures. we should go back to this. This is great stuff, and start learning a lot more about this, because this is fundamental, and this gives you great characteristics out of your systems and learning good things about code. I'm not going to go on about it. It's a whole talk on its own right. So, kind of now wrapping up in closing, there's something coming. What is coming? Is it winter? What's actually coming is the Internet of Things, and Internet of Everything, whatever you want to think. Depending on your point of view, it's going to be somewhere between 20 and 75 billion devices are going to be connected by 2020. Everyone's got a different view on it. I don't really care. What I do see all the time is volumes going up over and over and over. It's almost like we're not seeing percentage points, I'm seeing factor changes. I seen one client just even a few years ago who had 6 million concurrently connected devices in Italy of people betting on football games. These sort of things are happening now. It's really, really interesting. So what is that saying? Quite simple, is we cannot control the arrival rates. The arrival rates, we want them to happen. We need the arrival rates to happen because that's what's going to drive business. So we have to think about service times. I don't care about languages. I don't care about platforms. I don't care about any of that stuff. If I want a system to be responsive, I've got to care about the service times. Whatever I implemented it in, it doesn't matter. And if I can't sort the service times, I need to at least sort contention to do it in parallel. And the contention is probably going to be best answered by Jonas, who's taking the next subject. So on that point, thank you very much.
Wow.